In this video, we continue the discussion we had in the previous video about integration by algebraic substitution. So here, we will be discussing the last three types of integration by algebraic substitution. So type 5, when the integrand contains the expression of the square root of a plus bx plus x squared, but the radicand is factorable into two linear factors, alpha plus x times beta minus x, then we use the substitution that this quadratic a plus bx plus x squared is equal to the square of the first factor, alpha plus x squared times z squared, or this quadratic a plus bx plus x squared is equal to the square of the second factor, beta minus x quantity squared times z squared. And to illustrate this type of integrand, we will solve this example here. What is the integral of dx over x times the square root of x squared minus 3x plus 2 here? Now, we notice that our radicand, the expression inside the square root symbol, is factorable. So we write here x squared minus 3x plus 2 is equal to the product of two linear factors, x minus 2 times x minus 1. And you can check that these are the linear factors for this quadratic expression. So x times x is x squared. And to get the last term here, it's the product of the last term by the last term. So negative 2 times negative 1 is positive 2. And how do we get this middle term? This middle term is the sum of the products of the outers and the inners. So we have negative 2x plus the negative 1x. And the negative 2x plus the negative 1x, that's negative 3x. And since this quadratic expression is factorable, we use the substitution x squared minus 3x plus 2 is equal to x minus 2 quantity squared times z squared here. And the factors for this are x minus 2 times x minus 1. So this is equal to x minus 2 quantity squared times z squared. And we see here common factors from both sides of the equation. So dividing both sides of the equation by x minus 2, what remains is x minus 1, which is equal to x minus 2 to the power of 1 times z squared. So this is the simplified form of our substitution here. And distributing the z squared to this binomial here, we have x minus 1 is equal to x times z squared minus 2 times z squared. And grouping all the terms having x's to the right, we have 2z squared minus 1, because this term is negative at the right, becomes positive at the left. And this is equal to z squared x, this one, so I just write z squared first, minus x, because the positive x at the left becomes negative x at the right. And then we can factor out the x at the right hand side, the common x at the right hand side of this equation. So this is x times z squared minus 1. And dividing both sides of the equation by this z squared minus 1, we have 2z squared minus 1 over this z squared minus 1, which is equal to x. Then therefore, we have the representation of x, which is 2 times z squared minus 1 over z squared minus 1. And since we have the representation for our x, then we can solve for our dx here. That our dx is the derivative of this quotient here. So we square this denominator here. So z squared minus 1, quantity squared. And this denominator of z squared minus 1 will be multiplied by the derivative of the numerator, which is 4z dz. And this will be subtracted to the product of this numerator, 2z squared minus 1, times the derivative of the denominator, which is 2z dz here. So distributing this 4z to this binomial as well as this 2z to this binomial, we have dx, which is equal to the quotient of 4z times z squared, which is 4z cubed. And this is subtracted by 4z. And also this 2z times this negative 2z squared is equal to minus 4z cubed. And this is added to 2z here with a denominator of z squared minus 1 quantity squared here. So therefore, our dx is equal to the negative 2z, because this 4z cubed and the negative 4z cubed cancels each other. So what remains is this negative 4z plus 2z. And the result from these two terms is negative 2z with the denominator of z squared minus 1 quantity squared. Now, at this time, we have the representation of our x, which is this quotient here, and the representation of our dx, which is this one. Then we can use that one to substitute for this x and the dx in the integrand. But we don't have yet the representation of this square root of the quadratic. So we'll find the representation of the square root of the x squared minus 3x here plus 2. So this is just equal to x minus 2 quantity multiplied by z here from this substitution here. When you take the square roots of both sides of this equation. So substituting the value of our x, which is this one here. So our x is 2z squared minus 1 over the denominator of z squared minus 1. So this is our value of x, but this should be subtracted by 2. So minus 2 times our z here. Now, combining the two terms inside this bracket, we have our LCD, which is z squared minus 1. And this z squared minus 1 divided by z squared minus 1, the result is 1 times the numerator of 2z squared minus 1. And this z squared minus 1 divided by 1, it's z squared minus 1. And that will be multiplied to the numerator of negative 2. So negative 2 times z squared minus 1. And the whole fraction will be multiplied by z here. So simplifying further, we have this fraction of 2z squared minus 1 minus 2z squared plus 2. If you distribute this negative 2 to this binomial here, and this is divided by z squared minus 1. And we know that 2z squared minus 2z squared cancels each other. So what remains is 2 minus 1. So 2 minus 1 is 1 here. And this will be divided by z squared minus 1 times z. So therefore, we say that the value of the square root of x squared minus 3x plus 2 is equal to z over z squared minus 1. in terms of z. And now we can use our representations for x dx and this square root of this quadratic to our integrand here. So this is equal to the integral of our dx, which is negative 2z over the square of z squared minus 1 quantity squared dz. And this is divided by our x, which is this one here. So this is 2z squared minus 1 divided by z squared minus 1. And this will be multiplied by the square root of this quadratic, which is this one. So this is times z over z squared minus 1. So multiplying our fractional numerator by the reciprocal of the denominator, we have the integral of negative 2z dz over z squared minus 1 quantity squared times the reciprocal of this, which is z squared minus 1 over 2z squared minus 1 times z squared minus 1 over z here. And we know that this square of z squared minus 1 cancels with this 2z squared minus 1. And also this z cancels with the z in the denominator. So what remains is the negative 2 here, which can be factored out in front of the integral symbol. We have the dz over the denominator of 2z squared minus 1 from this one here. But the denominator can be expressed as a difference of two squares. So we have negative 2 times the integral of dz over the square root of 2z quantity squared minus 1 square, because this 2z squared can be expressed as the square root of 2 times z quantity squared, and this 1 can be expressed as 1 squared. So we can use our substitution a for the constant 1, and for our u we use to represent square root of 2z. So therefore we can solve for our du, and our du is the square root of 2 dz. So therefore our du is divided by the square root of 2 to represent dz. So we can now use for this representation of the square root of 2 times z as u, and dz as du over the square root of 2 for this one here, and the 1 for our a. So we can rewrite our integrand as the integral of dz, which is du over the square root of 2, and this is divided by the square of this one, which is our u, minus the square of our a here. So we can factor out our constant of the square root of 2 in this denominator as negative 2 over the square root of 2 times the integral of du over u squared minus a squared. And this is equal to the negative 2 over the square root of 2 times the integral of this, which is 1 over 2a times the natural log of the absolute value of u minus a divided by u plus a. And this is added to the constant of integration c, because we know this formula as the integration formula 25 in our previous video, in video lecture 5. So substituting back the values of u and a here from this representation, we have the negative 2 over the square root of 2 times 1 over 2a, but our a is 1. times the natural log of our u, which is the square root of 2z minus 1 over the square root of 2z plus 1. And this is added to the constant of integration c. But we need to express this z in terms of our original variable x here. And we can solve that from this equation here. So we write from equation x minus 1, which is equal to x minus 2 quantity multiplied by z squared. We can divide both sides of the equation by x minus 2. So we have x minus 1 over x minus 2 is the value of our z squared. So taking square roots of both sides of the equation, we have z, which is equal to the square root of x minus 1 over x minus 2. Thus, substituting this value of z here in our answer, we have the negative 2 over the square root of 2 times 1/2 of the natural log of the absolute value of the square root of 2 times the value of z, which is this one here, the square root of x minus 1 over x minus 2 minus 1 over this denominator of square root of 2 times z, which is this again square root of x minus 1 over x minus 2 added to 1 here. And this is added to the constant of integration c. And multiplying our constants, we have this negative 2 over 2 times the square root of 2 times the natural log of the absolute value of the square root of 2 times x minus 1. If you multiply the square root of 2 to the numerator here over the square root of x minus 2, and this is subtracted by 1 over the denominator of the square root of 2 times x minus 1 divided by the square root of x minus 2. So we add this one to 1 plus the constant of integration c. So combining these two terms in this numerator and these two terms in this denominator, we have this negative 1 over the square root of 2 times the natural log of the absolute value of our LCD in this numerator, which is square root of x minus 2. So we have the square root of 2 times x minus 1 minus the square root of x minus 2. And this is also divided by the LCD in the denominator, which is the square root of x minus 2. So we have the square root of 2 times x minus 1 plus the square root of x minus 2. And this is added to the constant of integration c. And multiplying this fractional numerator by the reciprocal of the denominator, their denominators cancels each other. So our final answer can be expressed as the negative square root of 2 over 2 times the natural log of the absolute value of the square root of 2 times x minus 1 minus square root of x minus 2. And this is also divided by the square root of 2 times x minus 1 plus the square root of x minus 2. Hence, this is our answer for this example here. Now, let's proceed to type 6 here. When the integrand contains this expression, the square root of this quadratic expression, then we use the substitution a plus bx plus x squared, our quadratic, to be equal to z minus x quantity squared. And we use this type of integration by algebraic substitution when this quadratic is not factorable to two linear factors. So we use this substitution: x squared plus x plus 2 is equal to the square of z minus x. And expanding the square of this binomial, we have z squared minus 2zx plus x squared. Then we notice that this x squared and this x squared cancels each other. So what remains is x plus 2, which is equal to z squared minus 2zx. And grouping all the terms with x's at the left side of the equation, we have x plus 2zx at the left side of the equation. And at the right hand side, we have z squared minus 2. Then we can factor out our common factor of x for these two terms. So we have x times 1 plus 2z. And at the right, we still have z squared minus 2. So dividing both sides of the equation by 1 plus 2z, what remains at the left is only x. So this is equal to z squared minus 2 over the denominator of 1 plus 2z here. So therefore, we can solve for our dx. And our dx is obtained by the derivative of this quotient here. So we have the denominator, which is the square of this 1 plus 2z squared. And this denominator of 1 plus 2z will be multiplied by the derivative of the numerator, which is 2z. And this numerator also of z squared minus 2 will be multiplied by the derivative of this denominator, which is 2, using the quotient rule for differentiation. So we have dx is equal to the quotient of this one, which is 2z plus 4z squared. When you distribute this 2z to this binomial here, and we have 2z squared plus 4. When you distribute this 2 to this binomial also here, with a denominator of the square of 1 plus 2z. Thus, we can combine these similar terms here, and our dx finally is equal to 2z squared plus 2z plus 4. And this is divided by the square of 1 plus 2z. So we can use this x and the dx in our integrand here. But we don't have representation for this term. So solving for this square root here, we can use this equation, which is the square root of this quadratic x squared plus x plus 2 if you take the square root of both sides. So at the right, we have only z minus x. But we have our x here. So this is equal to z minus our x, which is z squared minus 2 over 1 plus 2z. And finding the LCD of these two terms, we have 1 plus 2z. When divided by 1, it's 1 plus 2z. So this is multiplied to the numerator of z minus the quantity of z squared minus 2 here. Now, removing the parenthesis, we have z plus 2z squared when you distribute the z to this binomial. And removing also this parenthesis here, we have minus z squared plus 2. And this is divided by the denominator of 1 plus 2z. So therefore, we say that our square root of x squared plus x plus 2 is equal to this quotient here, which is equal to z squared plus z plus 2, because we can combine 2z squared and this negative z squared here. So divided by 1 plus 2z. Now, using this representation for this one and the representation for x and dx to our integrand, we have our integrand, which is the integral of our dx, which is 2z squared plus 2z plus 4 divided by 1 plus 2z quantity squared dz. And this is divided by our x, which is z squared minus 2 over 1 plus 2z. And this is multiplied by the representation of this square root, which is this one here. So we have z squared plus z plus 2. And this is divided by 1 plus 2z. And factoring the common factor for this trinomial here, we have the integral of 2 times z squared plus z plus 2. And this is divided by the square of 1 plus 2z. So multiplying this fractional numerator by the reciprocal of our denominator, which is 1 plus 2z over z squared minus 2 from this factor here times 1 plus 2z over z squared plus z plus 2 from this factor here. And we notice that we can cancel this trinomial with this trinomial, and the square of 1 plus 2z will be cancelled by these two 1 plus 2z's. So what remains is 2dz over z squared minus 2. And factoring these 2 outside the integral symbol, we have this 2 times the integral of dz over this z squared minus 2. But the denominator can be expressed as a difference of 2 squares. So we have 2 times the integral of dz over the square of z and the square of the square root of 2. And let our a be equal to the square root of 2, and our u is z here. So therefore our du is dz. And substituting our representations here, we have 2 times the integral of dz, which is our du, over the square of z, but our z is u, and also subtracted by a squared because the square root of 2 is our a here. And we know from our previous video that the integral of this is equal to 1 over 2a times the natural log of the absolute value of u minus a over u plus a, and this is added to the constant of integration c. And multiplying these 2 and 2a, we have 1 over a times the natural log of the absolute value of our u, which is z, and our a, which is the square root of 2 over z plus square root of 2. And this is added to the constant of integration c. And expressing the z back to our original representation of z, which is obtained from this equation when you add both sides of the equation by x. So our z is this square root plus x there. So we have 1 over square root of 2 times the natural log of our z, which is the square root of x squared plus x plus 2 plus x minus the square root of 2. And the denominator will be same as the square root of x squared plus x plus 2 plus x, but this is added to the square root of 2 plus the constant of integration c. And we say that this is our final answer for this example here. Now, let's proceed to type number 7. When the integrand contains this expression 1 over the binomial px plus q times the square root of a trinomial ax squared plus bx plus c, then we use the substitution of px plus q, this binomial, equal to 1 over z. And to illustrate this type, we will solve this example here. And since this radicand is of the form type 7, then we use our substitution of 2x plus 1 equal to 1 over z. And solving for x, we subtract both sides of the equation by 1. So 2x is equal to 1 over z minus 1. And combining both terms, we have our LCD of z. So this is 1 minus z in the numerator. And dividing both sides of the equation by 2, what remains at the left is only x. So this is 1 minus z over 2z. And therefore, we can solve for our dx, which can be obtained by the derivative of this quotient here. So we square the 2z as our denominator, and this denominator of 2z will be multiplied by the derivative of the numerator, which is negative 1. And this numerator of 1 minus z will be multiplied by the derivative of the denominator, which is 2. So, simplifying our fraction, we have negative 2z minus 2 plus 2z here, because negative 1 times 2z is negative 2z. But this negative 1, when multiplied by 2, the result is negative 2. And this positive z, when multiplied by 2, we have 2z. So this is divided by 4z squared when you square this 2z here. But we notice that our numerator can be cancelled here. 2z minus 2z is 0. So what remains is negative 2 over 4z squared dz. So our dx is equal to negative dz over 2z squared. And since we have the representations for our x and dx here, we need to represent also this trinomial. So we have 3x squared plus 2x plus 1 is equal to our 3 times the square of our x, which is 1 minus z over 2z. And this is added to twice of this x, 1 minus z over 2z, and then plus 1. And squaring this quotient here, we have 3 times the fraction of 1 minus 2z plus z squared. And this is divided by 4z squared here. And this is added to this term, so we can cancel this 2. So what remains is 1 minus z over z. So combining these 3 terms, we have our LCD of 4z squared. So this is 3 times this trinomial. So we have 3 minus 6z plus 3z squared. And this is added to the result when you divide 4z squared by z. And the quotient is 4z. So this 4z will be multiplied to the numerator of 1 minus z plus this 1 when divided by 1 is 4z squared. So that is our whole fraction. Now, distributing our 4z to this binomial, we have 3 minus 6z plus 3z squared plus 4z minus 4z squared plus 4z squared over 4z squared. So therefore, our trinomial, this one, 3x squared plus 2x plus 1 is equal to this fraction here. And we know that this negative 4z squared and positive 4z squared cancels each other. So this 3z squared from this one will be subtracted by 2z, because this is the result when you combine 4z and negative 6z. And this is added to 3 divided by 4z squared. So using this representation for x, for dx, and for this quadratic expression, we can substitute that one to our integrand. So this is equal to the integral of our dx, which is negative dz over 2z squared for this dx here. And this is divided for our denominator, which is 2 times x, but our x is 1 minus z over 2z from here. And the product is added to 1 to represent this binomial here, times the square root of our trinomial, which is this one here. So this is 3z squared minus 2z plus 3 over 4z squared. So simplifying our integrand, we have negative dz over 2z squared. But this is divided by this 2, and this 2 cancels. So we have 1 minus z over z plus 1. Taking individually the square roots of the numerator, we have the square root of 3z squared minus 2z plus 3. We know that the square root of the denominator is 2z. So combining these two terms here, we have negative dz over 2z squared when divided by these two terms, but when you combine, that is 1 minus z plus z, but this is multiplied by this quotient of the square root of 3z squared minus 2z plus 3 over 2z. Now, multiplying our numerator by the reciprocal of this denominator, we have the negative of the integral of dz over 2z squared times the reciprocal of this, which is z over 1, because this negative z and z cancels each other, times also 2z over the square root of 3z squared minus 2z plus 3. And we know that this z and 2z, when multiplied, cancels to this 2z squared in the denominator. So we have the remaining integrand of the integral of dz over the square root of this trinomial here, which is 3z squared minus 2z plus 3. But we can manipulate a little to make a square in this radicand by multiplying 3 over 3 in this radicand here. So we'll multiply 3 over 3 times the fraction of 3z squared minus 2z plus 3. And multiplying this 3 over 3, which is equal to 1, we have this negative of the integral of dz over the square root of this product, which is 9z squared, and this is subtracted by 6z plus 9 divided by this square root of 3, and this is equal to the negative of the integral of the square root of 3 dz over the denominator of 9z squared minus 6z plus 9, because when you multiply our numerator by the reciprocal of the denominator, we have this integrand here. So with this quadratic in our radicand, we can form a perfect square trinomial. And factoring out this constant of square root of 3, we have the negative square root of 3 times the integral of dz over the square root of our radicand, which is 9z squared minus 6z plus 1. And we do this so that we can formulate a perfect square trinomial. So this is added to 8 because the whole constant is 9 here. And now we can express this sum as a sum of two squares. So we have this square root of 3z minus 1 quantity squared. And this is added to the square root of 8 quantity squared. So by substitution, we can represent our square root of 8 as our a, and our u this time is 3z minus 1. So our du is 3 dz. So therefore our du over 3 is the representation for our dz. Now, substituting this 1 to our integrand, we have the negative square root of 3 times dz, which is du over 3 for this dz here, over the square root of our u. So we square our u added to the square of our a, because our a is square root of 8. And this is equal to the negative square root of 3 times 1/3 when you factor out this 3 here. And this is multiplied to the integral of du over the square root of u squared plus a squared. And this is so familiar to us from our video number 5 that this is equal to the natural log of u plus the square root of u squared plus a squared. And this is added to the constant of integration c. So substituting back our original representations, we have negative square root of 3 over 3 times the natural log of our u, which is 3z minus 1 plus the square root of our u squared, and our u is 3z minus 1. And this is added to the square of our a, which is 8. And solving for our z from this equation here, we have our z, which is equal to 1 over 2x plus 1. Then therefore, our 3z minus 1 is equal to 2 minus 2x over 2x plus 1. If you substitute the value of x, which is this one here, to this denominator. So substituting our value of 3z minus 1, which is this one here, we have the negative square root of 3 over 3 times the natural log of the value of 3z minus 1, which is 2 minus 2x over 2x plus 1. And this is added to the square root of the square of 3z minus 1 plus 8. And you can check that that is equal to the square root of 36x squared plus 24x plus 12 divided by 2x plus 1. So combining these two terms here, we have negative square root of 3 over 3 times the natural log of the fraction of 2 minus 2x plus the square root of 36x x squared plus 24x plus 12. And this is divided by the common denominator, which is 2x plus 1, added to the constant of integration, c. And this is our final answer for this example. And that's it. If you learned something today, please check out my channel for more videos like this and click subscribe. Click the notification bell below so you'll get notified whenever I'll be posting a new video. Don't forget to like this video to show your support. And always remember to math your way up. Thank you.